All right. This is, I forgot to put the number. This is number 6. All right. So it says at closest approach, Saturn is about 8.5 astronomical units from Earth. If the rings are 270,000 kilometers in diameter, um, what is the angular size as seen from Earth? Round the answer um, to the nearest whole number. No, I want it one place past. I don't know why it says that. It should just be one place past the decimal. Oh, there it is, right here. Um, we want the answer in the angular size in arc seconds. Um, yeah, I need to take that away. That to the nearest whole number. At any rate, in arc seconds, and we want it to round it to one place past the decimal. That's the proper way to do this. All right. So anyhow, it's going to turn out to be 43.7 arc seconds. All right. So let's figure out how to do this. All right. So we have this equation right here. The size of an object is equal to so it's going to equal. I just wrote the equation here. So the size of the object, which I called script L here, on the left hand side, is equal to pi over 180, pi over 180 degrees, times the distance to the object, times the angular size of the object. That's what alpha is. That's what this. All right. So if I rearrange this and solve for alpha, really, that's what they're asking for, alpha, and that's going to equal. So the 180 goes over. So it's going to be 180 over pi. We did this problem, a very similar problem earlier, and then it's going to be times L. Well, I'll just put this in parentheses. That doesn't really have to be in parentheses, but times L, the actual size of the object, divided by the distance to the object. And L and D both of these have to be in the same units. All right, they have to be the same units. All right, and all right. Well, they give us the L in kilometers, 270,000 kilometers. So let's convert the distance to Saturn. All right, so the distance to Saturn they give us as 8.5 astronomical units, and we know that in 1 AU there are 150 million, 150 times 10 to the 6th kilometers. All right, so that'll change it into kilometers. All right, so here let's get our calculator out, and we'll do this. All right, so here it is. All right, let's clear that. All right, oh yeah, and this is at the closest approach. All right, so 8.5. Remember, one astronomical unit is the distance between Earth and the Sun, but at this point in Saturn and Earth's orbit, they're 8.5 astronomical units apart, and so we multiply that times 150 million, which is times 10 to the 6th. So it's going to be this many kilometers. All right, so that's 1.275, and let's see, so times 10 to the 9th. 1.275 times 10 to the 9th. 1.275 times 10 to the 9th kilometers. All right, so that's what our D is. All right, and so alpha, so now we can put the number, we can put everything in here, is going to be 180 over pi. All right, and then times, what was L? Oh, there it is. 270,000 kilometers. All right, I put the km just to show you that it's going to cancel these. Divided by 1.275 times 10 to the 9th kilometers, right? So the kilometers cancel. And that'll give us an answer in degrees. right? And we're going to change that because it asks us what it is in arc seconds. All right, so we'll change that in just a second. All right, so I've got this number. That there it is. We're going to divide by that. Remember that number is the same as 1.275 times 10 to the ninth, right? So I'm going to store that in my calculator. Here we go. All right, so there it is. It's so I'm going to say 180 divided by pi. I shouldn't. With this calculator, you got to be very careful how you do. All right, so that's 180 divided by pi, and then I'm going to multiply by the numerator. So times 270,000. All right, so there it is, and then we're going to divide by what I just stored in my calculator. There it is. All right, and so that's the answer in degrees. All right, so 0.0121 or something like that. I mean, I'm going to leave it unrounded in my calculator, so it's 0.0121 degrees. That's a little degree sign. It doesn't look like one. And I know that in 1 degree, that's a degree, a little circle. It's supposed to be a little circle. There are 60 arc minutes, and in 1 arc minute, there are 60 arc seconds. Remember, 2 hash marks mean arc seconds. All right, so I just take this number that's in my calculator and multiply by 60 squared, and then I'll be in. So there's the number, and then times 60 squared, and that changes it into arc seconds, which in astronomy, that's a very convenient. All right, so there it is, 43.67, right? And so since the 7 is greater than 5, I round that up to a 43.7. Let's see, didn't I put that? Yeah, there it is right there. So the answer is 43.7. And of course, you could write the word, arc seconds, or you could use the double hash marks. That works too. All right, forget about. I don't know why I wrote that. All right, so anyhow, that's number 6. For number 7, we're going to use the modified version of Kepler's third law and the mass of Saturn to calculate the period in hours of the material in the inner and the outer edges of Saturn's rings. The value for the semi-major axis, the one for the inner ring is 90,000 kilometers, and the one for the outer ring is 136,000 kilometers. So first of all, I need those distances to be in meters. All right. So for A, so for part A, the distance. So I mean, all I have to do is just change this to times 10 to the third, right? The distance is, instead of 90,000, it's going to be 90,000 times 10 to the third. All right, and now that's in meters. All right, and then for B, it's the distance is so this is the distance for A. The distance for B that's supposed to be a B. Sorry, is 136,000. And you can just add 3 more zeros. It's the same thing, times 10 to the third meters, right? So now it's in meters, right? All I did is change the kilometers to meters, right? Because in 1 kilometer there are 1,000 meters, which of course means 10 to the third meters. All right, so we're going to use this. This is Kepler's third law, but solved for the period. All right, so I've got the 2 numbers, right? There's the number for A, there's the number for B. All right, and I'm just going to plug those 2 in. All right, so for A, So here's part A. It's the period is going to be that's supposed to be the square root of 4 pi squared times, so it's going to be 90,000 times 10 to the third. All right, now I've got to cube that. It's underneath the square root. It's cubed, sorry, not squared. And then divided by big G, which is 6.67 times 10 to the minus 11th. And then times the, see, they give us the mass of Saturn right here. 5.68 times 10 to the 26th. All right, there we go. All right, and of course it's in kilograms, so we're good to go. And then part B, it's the same equation, exactly the same. The square root of, so it's 4 pi squared, but of course it's a different distance. This is the outer ring is 136,000, and then I could put 3 more zeros, or e to the third, 10 to the third, and I've got to cube that. All right, that's supposed to be raised to the third, divided by the square root thing should go through 6.67 times 10 to the minus 11th, and then times the mass of Saturn, which is 5.68 times 10 to the 26th. All right, so we'll do both of these in our calculator. The key thing here is, do you see where it says, can you see why? Let me get this. Can you see why the rings cannot be solid? Right. The answer is, if the rings were solid, both these answers would be the same number, right? They would take the same amount of time to orbit Saturn. All right, so let me get my calculator, and we'll do this. I'm just going to plug the numbers in. All right, so. All right, so this is for A and B. I've just put the 4 pi squared in there. All right, so it's going to be times 90,000, 2, 3, and then times 10 to the third, and then raise that to the third. All right, and then I'm going to divide by big G here, which is 6.67 times 10 to the minus 11th. All right, I'm going to hit equals. I'm not doing the entire, so all I've done is this part right here. All right, and then I'm going to divide that by the mass of Saturn. All right, so divided by 5.68 times 10 to the 26th. All right, and then I have to take the square root. All right, so now if I take the square root. All right, and so that's the answer in seconds. All right, so if I take, so there's the number, whatever it was. I'm running out of time. All right, so you get an answer of 27,561.7 and more seconds. Divide by 60 squared, you get 7.65 or 7.7 hours. All right, let me do the next one. Let me pause it and do this. For the second one, you get approximately 51,197. Divide that by 60 squared, and you get, so it would take 14 hours. All right, so they cannot be a solid. The inner and outer rings would rotate at the same speed.